Hello, myself Daksha DC, working as assistant professor. Today I am going to discuss about the topic phase equilibrium for the course BSc subject chemistry and the paper physical chemistry. So this session contains one component system. We are taken as an water as an example, and another one component system as an sulfur. So I'm going to discuss it in the session only, that is the one component system of water here. One component system that will be in this water system usually. This is in a bivariant. It can be completely defined by specifying two variables. The variables are temperature and pressure. In this figure, water can exist in three phases, namely solid, liquid and vapor phases. Hence, there can be three forms of equilibria: liquid equilibrium with vapor, and the solid equilibrium with vapor, and solid equilibrium with liquid. Each equilibrium involves two phases. So once we are going to study the phase diagram for the water system, any thermodynamic standpoint of view, so then this kind of the curve we are going to see in that is OA curve, OC curve and OB curve. So here, that is the OA curve, that is what we called as a vapor pressure curve, and OB curve what we called as a sublimation curve, and OC curve, that is what we called as a fusion curve. So once we go for, that is the OA curve, that is what we called as a vapor pressure curve. So here, so when we go from O to A, as we move to that is O to A, then the any point you are going to indicate on that particular point, those points are equilibrium with liquid water into the water vapor. Therefore, this is an univariant. This is a univariant system or a univariant degree of freedom here. So once you know that, whenever that is for each vapor, only one temperature that can be attained. The degree of system that will be a univariant. By using a Gibbs phase rule, F is equal to C minus P plus 2, which is equal to C is the only one component, that is water, whether that will be in the solid form or a liquid form or in a vapor form, minus 2 how many phases, that is a liquid and the vapor state, that will be I have written here, and plus 2, that is the variables are 2. So once you know that, that's overall, which is equal to 1. Therefore, degree of the system, that is what we called as an only 1. So once, that is, you had taken any one of this verified standpoint by on this curve, that is X, I am going to take as that one. So if we increase the pressure along, that is XB, and you put in a constant, that will be a temperature constant in there, then whatever the water vapor, whenever that is you increase the pressure, then you will convert it into the form of a liquid. At the same time, if you decrease that pressure, then it come back to its water vapor. That's the same thing if you increase the a temperature and you kept a pressure constant, then that is whatever that is the liquid water is converted into as a water vapor, then again you have to decrease that one, it come back to its original one, that is as a what is the vapor to a liquid on that. So like that only, if we increase or a decrease of vapor pressure or an increase or a decrease of a temperature, then only all the whatever the line xb, xy or xz or xz, they're all equilibrium with water. And also a water means that is a liquid water, and also with the water vapor, all the whatever the point you are taken on the OA lines are all equilibrium with these two, that is equilibrium with liquid water phase and with liquid water vapor. Therefore, this line, that is a degree of variant which is equal to univariant. If we extended OA curve above, that is the 374 up to that one, it is above the critical temperature, there is no water exist on that. If you apply the Cauchy-Clapeyron equations on that, if a change in the pressure with respect to change in the temperature, then enthalpy of vaporization divided by T into Vg minus Vl. So R ln of P2 by P1 is equal to the enthalpy of vaporization divided by R into T2 minus T1 divided by T1 into T2. Like that, if we explain on that is, if we go for that is the OB curve, here it is also this also that is equilibrium, this curve also equilibrium with solid ice with the water vapor. So if you go for any verified stand point of view, if you take an S is there, so if you take an S, then if we increase the pressure, so by kept a temperature constant, and it will give rise to SM linear. So this, what happens to that, that is SM, that is whatever the water vapor it get it a solidified here. So once this will decrease the pressure, again it come back to as a water vapor. So like that only, if we increase the temperature here, so kept a pressure constant, then there will be a increase in the melting point of curve, RNA, what we call as a decrease in that, a decrease the a melting point of curve. So once that is you going to get, that is a decrease in the melting point, when you know that will be decrease the melting point of curve. So that is the same thing, if you reverse that one, that is a decrease the temperature, again it will come back to that will be in the solidify. So like that only it is also, once you are going to kept what is that pressure constant and decrease that one. So if decrease up to that absolute temperature R, that is OB, that will be extend up to that a absolute temperature, only pressure exists. Even though that is whatever that will be on that, you are going to point out any point out on OB curve, at that point that is indicate it will be a univariant, and that will be a equilibrium with a two phases, that is a solid ice with water vapor. The same thing if we go for the OC curve, that is what we called as an effusion curve. As they increase the pressure on that on OC curve, along OC curve, that curve inclined towards the pressure one, because of as the pressure increases, you are going to increase the melting point of ice. So therefore, if we go for any verified standpoint of view, here it also that will be a two phases equilibrium with each other, that is solid ice equilibrium with a liquid water. So once that will be all the OA and OB, that will be point at meet at the point, that will be what we called as an O. This O, what we called as a triple point. This system, it is a invariant system. These two systems, that is will be depending on that a particular temperature, that is 0.07 at 4.58 millimeter mercury vapor pressure, then this is what we called as a triple point. It will be variable with both temperature and pressure. By applying that is Gibbs phase rule, then F is equal to C, that is 1 minus whatever that will be a here, that will be a 2 phases. You cannot say that it is a 2, that is a triple, that is a 3 plus 2 here, that is 3 minus 3, that will be what happens, so that will be equal to 0. So this is what we called as an invariant system. So at O, if increase the temperature, if we increase the temperature along OA, then there is no change in that, sudden change that will be appear, because of due to whatever the temperature you are going to apply, that one that will be utilized for the conversion of solid into a, that will be a liquid water. So until that is the invariant degree of invariant system, that will be converted into a univariant, then the further increase of temperature, then that will be a curve, that will be a extend to that OA curve. So like that only, if we increase the pressure, so at triple point, that pressure utilized for the water to get vaporized. So therefore, further increase in the pressure, then only it will be that pressure utilized to undergone with the along the vapor, that is the OA or an OB curve. So this is the one of that, that's a fusion curve. Let's increase that, that will be a fusion curve, that will be appear. It means that it will increase the vapor pressure, and that then there will be the utilized for the formation of the ice, and further increase that, then OC curve, that will be you are going to appear on that. That is the same thing if you go for, that is the OA dash. This is also some of the system that will be formed this OA dash curve. This OA dash, that will be beyond the triple point. So it means that this one without forming a solidification. This one what we called as a super cold curve. The here, that is super cold curve means whenever you touches any point you touches the a solid ice here, that is all the whatever the super cold system become solidified. This curve what we call as the system is at metastable equilibrium. So whenever it is this metastable equilibrium along, that is the OA dash, it will be situated above, that is the sublimation curve OB. Yeah, this is the phase diagram of the water system. From that we can get any kind of, that will be whether what temperature and what pressure we are going to require to get any kind of the thermodynamic verified standpoint of view. So we can explain by using, that is the phase diagram. Thank you.